called? Definite integrals. Alright, I'll explain what the definite part of the integrals means here in a little bit. But if we wanted to find the area underneath the curve of this, we could create an infinite amount of rectangles, which we've talked about. And the rectangles don't even have to be the same width in theory. You could make that one, you could make this one. If you just add up, like, if each individual rectangle's height is f of c sub k is the notation, like that's how high up it is. And each individual width of the rectangle is change in x or delta x. We went from here, this x to that x, from that x to that x. I'll do it like using k's. F of c sub k times delta x sub k. Okay, so that would be how many subintervals you have. Like you could make 10, you could make 20, and so on. It's got the height of every rectangle, and it's got the width of every rectangle. Okay, and if we add all of the rectangle areas up, we would have the area between, like, say from A to B. Well, we've talked about creating an infinite amount of rectangles, and that would lead to something called an integral. So it's the integral of the function from A to B, and then each individual change delta x in calculus, we'll just call it dx. Remember, dx is the change in x, like in derivatives, dx. So this is called the integral. It's a definite integral because it has boundaries of integration. It goes from A to B. It will find the area underneath the curve from A to B, the area under the curve of f of x. Now the dx is not going to be used when we start evaluating them. Once we find, like using the fundamental theorem, we're not going to use the dx. It just tells you with respect to what we're integrating. So we're integrating with respect to x. Okay, so if I wanted to evaluate an integral, I could find the area underneath the curve. So this is out of your notes. I'll use the same example. So integral from -1 to 2 of x plus 1 dx. We're finding the area underneath the curve of a line from -1 to 2. So I'm going to make a graph of it. X plus 1 there's my line, y equals x plus 1. We're going from -1 to 2. So we're going from here to here. So we're looking for this area right there. That's the area between the curve or the function and the x-axis. Underneath the x-axis, it's considered negative area. So if it's above the x-axis, it's positive area. So this case, it would be 3 times, if I plug in 2 here, I get 3. So it's a triangle, 1/2 base times height, so we get 9/2 would be our answer. Okay, so the area underneath the curve, or the integral from -1 to 2 of x plus 1 dx is just 9/2. So that's the technique we're going to use today in 5.2, is to use geometry. It might be a half circle, it might be a rectangle, triangle, it could be, what's the trapezoid? There's a bunch of different geometric shapes, and we just use that in order to find the area under the curve. So that's not going to help us much when we have a curve like this. And we want to evaluate the integral. We need a better way, but today in 5.2, that's the technique that we're going to use. We're going to do an exploration, 5.2 number 1. So grab your books. It's on page 264. All right, so exploration 1, page 264. We're assuming that's a given to us. That's 2. So from pi to 2 pi, from here to here, then it would be -2, because it's the same amount of area just below the x-axis. Number 2, from 0 to 2 pi, from here to here, that'd be 0, because we've got a +2, -2, so it evens out to be 0. Number 3, from 0 to pi over 2, so that's from here to here. It chops it in half, so that'd be 1. From 0 to pi of 2 plus sine x, so we're taking sine x and we're shifting it up 2. Up 1, up 2, it's right up here. From 0 to pi. Did you get an answer for this one?
Yeah, we did.
You did or didn't?
You did.
What did you get?
We got 2 plus 2 pi.
Good. 2 plus 2 pi. Because the area underneath this curve, this is going to be a rectangle here, which is 2 times pi, so that's 2 pi. And we already know that that's 2. So we have 2 plus this rectangle is 2 pi, so 2 plus 2 pi. Number 5, from 0 to pi. If there's a 2 inside of an integral, if it's 2 sine x from 0 to pi, any constant, we can always remove it and put it on the outside. So that's 2 integrals from 0 to pi of sine x. So if you have a constant inside, you can pull it outside. We already know that's 2. So 2 times 2 gives us 4 for that one. Number 6, it's shifted everything 2 to the right. We start at 2. If you can imagine, this is your y-axis right here. All it is shifting it 2 to the right, and you're going to get the same area, so it's going to be 2. From negative pi to pi, from negative pi to pi gives you 0, because that's -2 and that's 2. From 0 to 2 pi of sine of x over 2. So sine of x over 2, if you remember, x over 2 means it's sine of 1/2 x. So if you remember back in your Algebra 2 pre-calc days, the period is always 2 pi over b, so it's 2 pi over 1/2, which is 4 pi. It's going to take 4 pi to complete. So if this is 2 pi, it's only half done. It's going to go and then keep on going. So what are we trying to do? From 0 to 2 pi, what's this? It'd be like going like this. And it's doubling the area. It turns out to be 4. We don't know how to do that right now. That would be where the intuition comes in. If the regular one is this, the double length one would be twice as much. Number 9 is 0, just as much above as below. And number 10 is 0. What kind of function about from negative k to k? Like if I had an odd function, if you notice this sine x is an odd function, it looks the same upside down. You're always going to have just as much area above as you do below because of the nature of it being odd. So if I had a cubic that's odd, like this, as long as we're going from the same, like from negative k to positive k, you're always going to have the same amount of area above and below, so it'll always be 0. Questions on that? All right, let's look at exploration 2, page 266. All right, so what kind of discontinuity is? There's removable, there's jump, there's infinite, there's oscillating discontinuity. Usually, I mean, there's a lot of books that just consider them removable or non-removable. So let's figure out if that's removable or not. Removable means that there's a factor on top and bottom we can divide off, which is the case here. I've got an x plus 2, x minus 2 on top, so the x minus 2's do divide off. So it's essentially the line y equals x plus 2. The only difference is this function here has an infinitesimally small hole where? At what x value? At 2. Very good. Okay, so this makes a hole at 2. So it's the line except for at 2. Okay, so part A says, why is it not continuous? Well, because 2 makes the bottom 0, and that is removable discontinuity. So use areas to show that the integral of f of x from 0 to 3 is 10.5. Okay, so maybe this will be an explanation to kind of do together. So if I was going to graph x squared minus 4 over x minus 2, I'm just going to graph y equals x plus 2. Because it's the same thing, except there's a hole in the graph. So there's my graph, and at 1, 2, 3, we're looking for all of this area, except at 2, there, I gave it a little tiny hole there. Okay, so we want to know what the area is between 0 and 3, that shaded area right there. So we get a trapezoid. Area of trapezoid equals 1/2 base 1 plus base 2 times the height. Or you could always just chop it up into a rectangle and a triangle. So it has this base and this base. Bases are always parallel with each other, and the height is the distance between the two bases. So 1/2 base 1 is 2, base 2, well, when I plug 3 into the equation, I get 5, so that means that height is 5, this height, and then our trapezoid height is 3. So 7 times 3 divided by 21 over 2, which is 10.5. And that's what we were trying to prove, that it has an area of 10.5. Greatest integer function from 0 to 5. Alright, I'll go through that kind of quickly too. We're integrating greatest integer of x from 0 to 5. So if you have a graph of greatest integer, then we're in pretty good shape. Remember, the greatest integer is a stepwise function. 1, 2, 3, 4, 5. 1, 2, 3, 4. If I was graphing the greatest integer of 0.5, what would it be? Maybe you don't remember the greatest integer function. Yeah, exactly. Yep. So the greatest integer of a half, we always round down, so it's 0. So the greatest integer of 0 is 0. Greatest integer of half is 0. Once I get up to 1, the greatest integer of 1 becomes 1. Greatest integer of 1.5 is still 1. It remains 1 until it gets to 2. Then it jumps up here. So you can see why it's called a stepwise function. Alright, so if we're going to find the area from 0 to 5, we want to add up all of these rectangles. So 1 by 1 is 1, 1 by 2 is 2, 3, 4, so 7, 8, 9, 10. So our answer would be 10, because that's the area underneath the curve from 0 all the way to 5. Oh, they tell us, use areas to show that it is 10. There. Alright, let's use our calculators. The last thing I'm going to show you today is how you can use your calculators to do some work for you. That's always a good thing. So let's see, let's find the integral of, I don't know, x squared minus 2 from 0 to 4 dx. All right. So we don't know how to do that right now without using RAM, because it's not going to produce a geometric shape that we have a formula for. But the good news is our calculator will do it for us. So we're actually going to learn how to do it on a calculator before we know how to do it by hand. All right, so we're going to go to math. Get up. There we go. So you could do derivatives and you can do integrals. I don't know if I showed you derivatives. Yeah, I showed you derivatives on here. Function integrals. We're going to do that. I hit enter and it creates our integral. Now if you had an older calculator, it won't be in this syntax. Let me know if you're getting like a bunch of parentheses, and I can help you with that too. Okay, so we're going from 0 to 4, and it's x squared minus 2, and it's always dx. It's really helped when the calculator shows you that. Like before, you had to do something, comma, like 0, comma, 4, comma, x squared minus 2, comma, x. So a whole bunch of commas here. You can just type it in. I'm going to go math, enter, enter, because I don't like decimals. And we get 40/3. Okay. Another way of doing area under the curve, a cooler way, but probably not a way that you'll do all the time. I'm going to graph y equals x squared minus 2. And now I'm going to calculate right up here. Calculate an integral. And it wants a lower limit, which is a, so 0, an upper limit, which is 4. Hit enter. And look at that. So 13.33 gives us our answer, and it shades it for us. No oohs and ahs? No? Oh. I was kind of hoping for a little more than that.
Can't wait to do that later.
There we go. That's what I was looking for.